press the bell icon on the YouTube app and never miss another update.
Hello children, we are discussing atomic structure. And we are in part 12 of this chapter. Atomic structure. So in our last class, we discussed about the Rydberg's formula. What was that? Wave number equals to RH Z square into 1 by N1 square minus 1 by N2 square, where Z is the atomic number and RH is the Rydberg's constant with the value 109677 centimeter inverse. In hydrogen spectrum, as I mentioned, we have different series obtained when the hydrogen is irradiated, excitation of the electrons comes into play, and when the electrons are coming back, transition is happening back, electrons are coming back from excited level to the ground states. There are 1 mole of electrons in 1 mole of hydrogen atoms, 1 mole of electrons. When these electrons will get excited, naturally, these electrons will not go to the same energy levels. They may be excited to different energy levels. Means transition can occur from 1 to 2, 1 to 3, 1 to 4, 1 to 5, or when the electrons will be coming back to the ground state, they may be coming from, suppose they shifted from 1 to 5, but they may be coming from 1 to 4 only. So the ground state of the electrons will keep differing. On the basis where the electron is coming back after getting excited from its ground state, where the electrons comes back and which is the new ground state for the excited electron, different series in hydrogen atom have been found. We call that as line spectrum of hydrogen. As I mentioned in my previous class, there are different series that we have available. Now let me give you a molecular interpretation of it, what exactly it means. Say children, we have hydrogen atom, and as we know, electrons will be rotating it according to Bohr's model. I mentioned down centripetal and centrifugal forces being balanced. So these are different shells in an atom we have. This is K, this is L, this is M, this is N and O. According to mathematical equations I have shown, energy of each shell in hydrogen atom is minus 13.6 into Z square by N square electron volts. Right. So once energy is given, electron can be excited from K to L, K to M, K to N, K to O. And when the electrons are coming back, what will be happening? As the electrons will keep coming back, so from 1 to 2, from 1 to 3, 1 to 4 or 1 to 5. If I suppose this is the shell that's outermost or out of atom, that's infinity. So electron can be shifted from 1 to infinity as well. Good. Now you can see a very simple relationship. When transition is happening, energy levels, energy difference between the two will be delta E will be E2 minus E1. Technically, if I write, it will be E final minus E initial. That means when the electron will come back from excited state to the ground state, it will lose energy in terms of discrete values, and the energy released by it will be quantum, which will be given by delta E, which should be equal to h nu or hc by lambda. Correct or not? So every emitted quantum of energy will be pertaining to specific wavelength and it will be pertaining to specific frequency. Where exactly the electron is coming back after emitting the energy, we have different series depending upon where exactly the electron is coming back after absorption of energy. One thing that you should bear in mind is that as the excitation is to happen to the higher energy levels, the frequency will also keep on increasing. You can see that very clearly here. Because the amount of energy that will be required to do this will be more. So frequency will keep on increasing. So this will have less frequency compared to second, compared third, compared fourth, compared fifth. And when you see the wavelengths will be decreasing and energy will keep on increasing. What I mean to say is, when electron is coming back from second energy level to the ground level, or it is coming from third energy level to the ground level, the wavelength of this one, suppose if I say wavelength 2, it will be definitely less than that of wavelength 1. So the photon emitted out when the electron is coming from higher energy state to low energy state will have varying energies. More the difference between the energy level, that is n initial, where the electron is actually coming back, and to the excited level where from it is coming back. If the shells are very far from each other, then high energetic photons will be released. I will explain these things one by one. Am I clear here? So if now children, I'll say now electron is getting shifted from 2 to 1. Naturally, what will be the wavelength required in this case? Will be less compared to wavelength from 2 to 3, because energy requirement from 2 to 3 is less compared to 1 to 2. I have already told you that cases delta is equal to E2 minus E1. Now this is one way of showing how exactly in atoms the hydrogen spectrum we are discussing, children. Hydrogen spectrum applicable to hydrogen atom and hydrogen like species. Okay. Now if I show a higher energy setup of this in terms of energy levels, how will this series look like and how exactly will this come into play? Have a proper look on this, children. Careful examination. Right. Let's have a look how it looks like. Okay. So I'll draw energy levels here. Then you have, consider this to be, this one to be N1, this is N1, then I have shown second energy level. I am giving you a deeper detail of this. A while earlier I showed you at the atomic level. We can have infinite number of shells in an atom, as we know from the quantum numbers. And this one, suppose this is infinity. Okay. As the electron has been excited, after some time it will, once excitation has been stopped, it will start to give energy. As it emits out the energy which is analyzed, and it falls back to ground level 1. I have already told you in Rydberg's formula. So when the electron is coming from higher status and the ground level where the electrons are coming is N1. Suppose this is N1, this one is N1, N2, N3, N4, N5 energy level, N6, N7, N8, N9, so on and so forth up to infinity. So electron is coming from higher energy status to lower energy state, means high energy levels to low energy levels by emitting energy. In this series, you can find out excited energy levels are 2, 3, 4, 5, so on and so forth. And the ground state where the electron is coming is 1. So this series is called as Lyman series. What do we call this as? Lyman series. So for Lyman series, children, what is ground state N1, that is N initial, is 1, and what is N2? It is can be more than 1, 2, 3, 4, 5, 6, up to infinity. So this Lyman series. Now when the electron is coming from 2 to 1, it will emit energy or not? Yes. 3 to 1, 4 to 1, 5 to 1, 6 to 1. You can see that as the electron comes from higher energy levels, when the ground state energy level is same where the electron is actually coming. So here you can find out the energy released when the electron comes from N2 to N1 will be less compared to that of 2 to 1, compared to that of 3 to 1, compared to that of 4 to 1, 5 to 1. We have learnt it already, right? In our mathematical equations we learnt earlier only delta E difference, energy differences. So in Lyman series, when the electron is coming from N1 for us is 1, right? And what is N2? What are the final energy states? We got 2, we have 3, we have 4, we have 5, we have 6, 7, 8, so on and so forth up to infinity. Remember, when the emission is happening from the electron in such a way that it comes from 2 to 1, this is called as alpha line of Lyman series. What line? Alpha line. So similar way, every series that we are going to discuss will have their alpha line. When we are coming from 3 to 1, it is called as beta line. When it is from 4 to 1, it's called as gamma line. When it is from 5 to 1, it is called as delta line, so on and so forth. And the last line, when the electron is coming from infinity into that shell 1, because here we are talking about which series? Lyman series. This one is called as limiting line. This is called as limiting line of the series, because this emission of the electron will end that particular series, and after that a new series is found, which we have already told you, where it's called as which series? Which series when N1 is 2? Balmer series. So for Lyman series, children, what is N1? 1. And what is N2? 2, 3, 4, 5, so on and so forth. So you got alpha, beta, gamma, delta line, and you have got limiting line. First line is called as alpha, then beta, then gamma, then delta, so on and so forth. And last line is called as limiting line. You can see that very easily. In this series, within the series, what is happening to the energy? The amount of energy released will be more when it is coming from infinity to 1 compared to 2 to 1. So children, when you are moving from alpha line to infinity, that is alpha line to limiting line of particular series, the frequency of the emitted photon will keep on increasing, wavelength of the emitted photon will keep on decreasing, energy of the emitted photon will keep on increasing. That means the limiting line will have the highly energetic photon compared to alpha, beta, gamma and other lines respectively. Am I clear or not? Am I clear? So if you are asked tomorrow, what will be the ratio of wave numbers? Understand it. What is the ratio of wave numbers for the alpha and beta line of Lyman series? What is the ratio of wave numbers for alpha and beta line? This is called as alpha line and this is called as beta line. First line is alpha, second one is beta. We know the formula, children. What is wave number equal to? It is equal to RH Z square into 1 by N initial square minus 1 by N final square. Our question is which line? Alpha line and beta line. So what will be wave number of alpha line equal to for which series? For which series? Lyman series. So alpha line will be RH Z square into 1 by, what is the initial energy level? 1 square minus 1 by 2 square, that is 4. So that will make it wave number of alpha line will be RH Z square into 4 minus 1 by 4. Wave number of alpha line will be RH Z square 3 by 4 centimeter inverse. This will be the wave number of which line? Alpha line. Can you calculate for beta line now? Now very simple. So this is for alpha line. What about V beta? Wave number of beta line. Which line? This is beta line. Transition is from 3 to 1. So RH Z square into 1 by 1 minus 1 by n square. What is that? N final. 3. That will be 9. So wave number of beta line will be RH Z square. It will be 8 by 9. Now what's the ratio of the two? Tell me the ratio of the two. Faster. What will the ratio of the two? Ratio of the two will be wave number of alpha line by wave number of beta line. For which series? Lyman series. Wave number of alpha line by wave number of beta line of Lyman series will be what? RH square. RH square will be off. So what remains here? 3 by 4 centimeter inverse. Here 8 by 9. So it will be 3 by 4 into 9 by 8. That makes it what? 27 by 32. So you can solve this out. This will be the ratio of the two. But which line? Alpha and beta. Similar way, if you are asked for the calculate the wave number of limiting line of which series? Lyman series. Limiting line of Lyman series. So for limiting line of Lyman series, what do we have here? What is mean by limiting line of Lyman series? Yes, children, faster. Which line now? Limiting line. Which series? Lyman series. So what is N1 here? 1. And what is N2 here? Infinity. Tell me wave number of limiting line LL will be equal to RH Z square into 1 by 1 square minus 1 by infinity square. Anything divided by infinity is 0. Wavelength of limiting line will be for hydrogen, what is Z value? 1. Wavelength of limiting line will be RH. And what's the value of RH? 109677 centimeter inverse. So wave number of limiting line will be 109677 centimeter inverse. You can see that very easily here. So it is 3/4 of what? RH value. Which line? Alpha line. What about beta line? We calculated a while earlier. 8/9 of. So that's very good thing that you can also take in mind. So wave number of alpha line, which series? Of Lyman series equals to what? RH into 3/4. So 3/4 of RH. Then 3 by 4 into RH. Oh yes, wave number. So when frequency is more, wave number will be less or more. Okay, then wave number of beta line is how much? RH into 8 by 9. So 3 by 4 some decimal value, RH into decimal value will reduce the value or not, or increase. The next one, wave number of limiting line is equal to RH. Wave number of limiting line, this is alpha, this is beta. Limiting line will be how much? RH, that's it. So we know when frequency is more, wavelength is less, energy is more. So when wavelength is less, wave number will be more because they are inversely proportional. So if wavelength is decreasing, frequency should be increasing, energy should be increasing, wave number should be, faster children, increasing, then so on and so forth. Did you get the equations clear? So you can calculate what? Wave number also, wavelength also. Whatever the value of wave number you are getting from here, inverse to that will be wavelength, because wave number equals to 1 by lambda. Instead of that you can write 1 by lambda, so RH value will be inversed. So this is which series? Lyman series. Remember children, in Lyman series ground state is what? N1, and excited states are what? What's the excited state that we have here? 2, 3, 4, 5, 6, 7, so on and so forth. So according to Rydberg's formula, for Lyman series of hydrogen atom, initial energy level is 1 and higher energy levels will be more than 1. That is 2, 3, 4, 5, so on and so forth. Next one. When the excited electrons which are there come from excited levels to ground level, and here now the ground state is 2. That means electron is now coming from higher energy levels and it is now stopped at energy level 2. Got it or not? Now if it is stopped at this energy level 2, we can, here also children, one more thing that I want to mention out here is with respect to Lyman series only. So because if I discuss with respect to Lyman series, other series should be understood very clearly by you. Okay, so say if the electron is coming from energy level 5, that is N1 equals to 1, because we are talking about Lyman series, and N2 equals to 5. That means emission is occurring from 5 to 1. You can see that easily. When it comes from 5 to 1, it is not necessary it will shift in only one line. This one line may further be made up of other small lines. That means when emission occurs, electron can come from 5 to 4 or from 4 to 3, then 3 to 2, 2 to 1. Yes, so this one line will be happening in how many jumps? It will happen in 3 jumps. That means this one line that is observed to you is further finely composed of many other small jumps. Those can be present here. So in Lyman series, if you want to find out what is the number of spectral lines produced, so which line it is? 1 and to 5. So alpha, beta, gamma, it is delta. So this will be delta line we are talking about. When I say line, I mean to say the energy released out. Keep it in mind. It's nothing like line. Okay. So here we are, what did I mention out? Number of spectral lines. So number of spectral lines. When electron emits energy. So what is the number of spectral lines produced when an electron will emit energy? So this particular line will be, see, if it is from 1 to 2, it's very simple. Say if it is from 2 to 1, if it is coming from 2 to 1, there is no intermediate jump possible, because children, all energy levels are not possible. Only those energy levels are possible where in the amount of energy released will be in discrete quantities and angular momentum should be nh by 2 pi. Am I clear? So it should be in terms of some particular frequency values. So when it is coming from 2 to 1, then the total number of lines produced is only 1, because this one line is the only line that is possible here. That is the only one emission that is possible there. When it is coming from 3 to 1, there are two possibilities. It can come from 3 to 2, 2 to 1, or it can come from 3 to 1 or 3 to 2, 2 to 1. So this may be further composed of many other jumps itself. It's like jumping from top floor directly to the ground, or jumping from top floor to the third floor, then to second floor, then to first floor. So top means from the top floor, if you are jumping directly on the ground, this is one jump. That means one emission. Only one type of photon will be emitted. However, if you jump it from one place to the next story, to the next story, so the full one band, one jump is further composed of small lines. We call those lines as fine lines. Am I clear? Good. So you can see here, number of spectral lines produced as is visible to us is only 1. You can calculate it by, so number of spectral lines equals to N2 minus N1 plus 1 into N2 minus N1 divided by 2. So it is N2 minus N1 plus 1 into N2 minus N1 divided by 2. N2 is the final energy level, N1 is the ground level. So if I do it for alpha line, so what is N2? 2. So it will be 2 minus 1 plus 1, because N1 is 1. So N2 minus N1 is 2 minus 1 divided by 2. So that will make it what? 1. So that will be 2 by 2. That's equal to what? 1. This is the one spectral line that you will get when electron directly comes from 2 to 1. It's very simple. Now if it is coming from 5 to 1, what I mentioned here. If it is coming from 5 to 1, how can we calculate it? Number of spectral line is produced equals to what? N2 minus N1 plus 1 into N2 minus N1 divided by 2. That will be 5 minus 1 plus 1 into 5 minus 1 divided by 2. That makes it 5 into 4. Right? Divide by. That's how many lines are possible here? 10 lines. So this jump can happen in how many jumps? 10 jumps. That you can see here. 5 to 4, then 5 to 3, then 5 to 2, then 5 to 1. Or we can write 4 to 3, then 4 to 2, then 4 to 1. Or 3 to 2, then 3 to 1. Or 2 to 1. So count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are possible 10 jumps that can happen. So these are possible emissions that can happen. It is coming from one energy level to other energy level itself. So directly you can calculate the number of spectral lines produced here. And when it is Lyman series, can we use this formula also? What is it? When it is Lyman series, n into n minus 1 divided by 2. Because our n1 is 1. So what is n value? 5 into 5 minus 1 divided by 2. That is 5, 4, 20. So that's again 10. So remember, for Lyman series, basic series, Lyman series, you can apply the formula n into n minus 1 divided by 2 because n1 is 1 there. However, any other series you cannot use n into n minus 1 because n1 is measurable there, 2, 3, 4, 1 and so forth. I hope I am clear with the statements here. So whenever you are calculating wavelength, wave number of different lines of Lyman series, you need to understand what is n1 and what is n2. You need to comprehend clearly that as the emission is happening from higher energy levels in Lyman series, the amount of energy released by photon, means the amount of energetic photon released will be higher. The frequency of that photon will be less. The frequency of that photon will be more, the wavelength will be less. That technically means when we are moving from alpha line to beta line to gamma to delta to theta to eta, so when you are going along this direction, wavelength of the emitted photon is reducing and frequency is increasing from first line to limiting line. This is called as starting line, this is called as limiting line. Within this Lyman series is exhibiting its properties. Did you understand Lyman series? So did you understand how to calculate the individual jumps that are possible in a particular line? So technically children, one line will be one band for you. One line will be one band. When I say one line, I mean to say when the electron is coming from excited to ground level, this will be produced in a band, and this particular band will be composed of many small jumps as well. It's like a muscle, skeletal muscle, which is made up of small fibers itself. Oh, is it clear or not? Did you follow my point here? So like one muscle here, and then this is made up of small segments itself, and we have a specific name as well in biology. What's the name? You can have a look. So this series is what series, children? Lyman series. So in Lyman series, what is ground state? N1. Now, this Lyman series exists in ultraviolet region of spectrum. So in hydrogen atom, this Lyman series wherein the ground state is N1 is present in which region? It's present in ultraviolet region. Okay. Now the next series that is available to us is, children, if excitation has happened and the ground level where the electrons are coming back, that is after emitting the energy, they are coming back to ground level 2. So basic ground level, that is N initial is 2. So electron is coming from higher energy levels and it is coming to 2. So this is first line. This will be second line, that's alpha, beta. This is gamma. This is delta. This is eta. This is theta. So on and so forth till we have the last line. And what is this line called as? What is this line called as? Limiting line. Right, children? So this one will be alpha. This is beta. This is gamma. This is delta. This is theta. This is eta, so on and so forth. There are so many names for it. So keep it in mind. If the question comes tomorrow, calculate the wave number of the theta line in a subjective question in JEE advanced exams. So calculate the frequency, wave number and wavelength of the eta line of Balmer series. You should be able to understand what exactly eta line means, which spectral line it is, which transition it technically means, right? So this series is called as Balmer series. Which series, children? Balmer series. Very good. So in Balmer series, now children, tell me, in Balmer series, which series? Balmer series. What is N1 for us? 2. And what is N2? More than 2. That is 3, 4, 5, 6, 7, so on and so forth. So you should understand 3 to 2, first line, 4 to 2, second line, 5 to 2, third line, 6 to 2, fourth line. This will be fifth line. This will be sixth line. So this is which line? This will be first line. This is second line, third, fourth, fifth, sixth. And if it is infinity, we call that as what line? Limiting line, last line. And in hydrogen spectrum, this series exists in visible zone. Which series? Balmer series. That's in hydrogen spectrum. We are able to see the series. We are able to see the colors. That comes from which series? That is technically which series? Balmer series. And this was the first one to be observed in hydrogen because it could be seen. And experimentally, after deducing out the formula for this, a general formula which is Rydberg's formula was found out. And Rydberg's formula I have written many times so far. So in Balmer series, what is N1, N2, so on and so forth. So values keep on changing. So next series is called as Paschen series. Which series? Paschen. In Paschen, rest of the things are same. You need to calculate energy wise if you want to go, stability wise you want to go. You can easily go into this discussion now. So what will happen to wavelength? Wavelength will decrease, frequency will increase, energy will increase, wave number is also increasing within the line as well. Yes or no? Now if you are asked sometimes a question, calculate the ratio of wave numbers of alpha line of Lyman and Balmer series. Calculate the ratio of wave numbers of alpha line of Lyman and Balmer series. It should be understood. Alpha line of Lyman series is transition from 2 to 1. Alpha line of Balmer series is transition from 3 to 2. Yes, so you can relate the energies of the two as well. If it is coming from 2 to 1, here it is coming from 3 to 2, energy differences will not be same because here it is more close to nucleus, it is far from nucleus. That is the reason you can also understand this is present in which zone? Visible zone. This is present in which zone? Ultraviolet zone. So if you compare alpha line with alpha line, you compare beta line with beta line, then 100% the energetic photon produced in the Lyman series will have more energy compared to that of the same line in which series? Balmer series. It is understood. On the whole, if you go children, you are moving from ultraviolet to visible to infrared zone. Do we have other series present as well? Yes. When the ground state is 3, so 2 to 3, 2 to 4, 2 to 5, 3 energy level, 4 to 3, 5 to 3, 6 to 3, then you have 7 to 3, then 8 to 3, then 9 to 3, then infinity to 3. This is called as this series, children, is called as Paschen series. What series? Paschen series. Whatever the rules I told you in Lyman series, same is applicable to this as well. So in Paschen series, so if you write down here anywhere, so in Paschen series, what is N1? When you look on Paschen series, what is N1 for us? N1 is 3 and N2 is more than 3. So N1 is 3, N1 is 3, okay, and N2 is more than 3. For which series? Which series? Paschen series. Then you have one more series that is called as bracket series. Here the emission of energy occurs and electron is coming from higher energy levels. And what is the ground state for us? 4. Which series, what I call this series as? It is Lyman, Balmer, Paschen. This one will be bracket series. Which series? Bracket series. So in bracket series, what is N1? So what is N1 in bracket series? 4. What is N2? More than 4. Which series we have got? Now next series is, I'll just extend it a bit so that I can draw the diagram. Okay children, so what's the next series which is available to you? Then next, what's the ground level? 5. Excellent children. So what is N1 here? 5. And what is N2? So N1 is 5 and N2 is more than 5. This is called as P-fund series. P-fund series. And then if you have N1 as 6, so what is N1 here? 6. And what is N2? More than 6. This is called as, this one children, I'll write it here. This is called as Humphrey series. What is that called as children? Humphrey series. So what are the different series we have? Lyman, then Balmer, then Paschen, then bracket, then P-fund, then Humphrey series. So keep it in mind. What is the ground state? What's the excited state in different energy levels? So this series, which is Balmer series, was existing in which one? Balmer series is existing in which zone? Visible zone. And these all the 3 series are present in infrared zone. So you can have far infrared and other things after that. Got the line spectrum of hydrogen clear? So in the lines, if you want to calculate the energy differences also, you should be easily able to do that. What is meant by alpha line, beta line, gamma line? What is meant by the energy considerations? What is meant by their wavelengths? What is meant by their frequencies? How to calculate all these according to this analysis, according to diagrammatic analysis that we have done here, children. I hope you have understood this series very clearly. So this is explainable in terms of energy. Even if you want to find out the energy difference, the rule remains the same. Delta I equals to minus 13.6 into Z square by N square. Energy differences if you want to find out between the lines. So within the same series, if you want to find out the energy difference of transitions, then simple. It will be minus 13.6 by 4, again the same one. Energy, it's actually same. Energy level 1 to 2, energy level 1 to 3, energy level 1 to 4, so on and so forth. The only thing that you need to understand clearly and understand comprehensively is what exactly the line is, which series exactly it is, and how do you relate the energy with the transition. So more the difference of energy levels between the ground state of that series and excited states, more will be the energetic photon emitted when the electron is coming from higher energy level to ground state. Am I clear with this thought? This is line spectrum of hydrogen. So if this is understood to you very carefully and very clearly, then we can have a numerical practice in our next classes. So next class when I will start complete the competitive part, means competitive part of basic fundamental of competitive part is already done. Questions with respect to these concepts that we have learned so far. So numerical practice we'll do in our next class. Am I clear with this? Clear to all? So I don't want to comprehend it and continuously put some numericals here only so that you will be in confusion. First of all, try to understand this hydrogen spectrum in terms of a different series. First, make sure at home you are writing very clearly and cleanly lines, different series, which series it's existing in, what transitions are happening, and yourself also you can think when electron is coming from high to ground level. So if you find out the ratio of the alpha line is ratio of the beta lines, or ratio of the alpha line and beta line of 2 different series or of the same series, you can try this question so that we can do our competitive questions. Why? clearly. Am I clear? So these are fundamental, basic, theoretical and competitive exam wise fundamental parts of this spectrum of hydrogen, which is line spectrum of hydrogen. So keep it in mind. Wave number formula, Rydberg's formula also it's called as V equals to RAZ square into 1 by N1 square minus 1 by N2 square. In order to find out how many lines a particular transition is made up of, the number of spectral lines of any series can be found out. So if you are asked to calculate the number of spectral lines of gamma line of Paschen series, gamma line of Paschen series, this is Paschen series, this is which line? Alpha, this is beta, and this one will be which line? Gamma line. So you can easily find out in gamma line what is N2 for us? 6, and what is N1 for us? So first of all try to understand its basic theory, and after that we'll continue the class. Thank you children.